Okay, let's do another example. And as a note, there's a term called Exergy Destruction, which we're going to run into quite a bit. I just think it would be the coolest band name, like some sort of like physics band. I could deal with that, okay? But let's do the problem now. So we have a geothermal power plant. It uses geothermal liquid water at 150 degrees Celsius. And it's at a rate of 250 kilograms per second. You're like, how is the water that hot? It's really highly pressurized. So I can stay a liquid even at high temperatures. Okay, so that's my heat source. It then produces 5.1 megawatts of net power in an environment, hey, this is what we're comparing to, of 25 degrees Celsius. It also says that 7.5 megawatts of the Exergy that's entering the plant is destroyed within the plant. Okay, so we want to find out how much Exergy is actually entering the plant in the first place and how much is exiting the plant. So let's get to it. So first off, let's check the steam tables. So we're going to assume that the water in the environment that we're expelling this into is just a saturated liquid. You're like, what if it's compressed? It doesn't matter. It doesn't change the enthalpy. It really doesn't change the properties that much if it's slightly compressed or subcooled. So we're just going to go with a saturated liquid. For this one, since it says it's geothermal liquid water, we're assuming that it's not some sort of saturated mixture. It doesn't make sense for it to be a saturated mixture. And so its quality would also be 0. So we have two temperatures. We know the quality. We would just be looking at the properties, and these would be the HF properties because it is, and the SF properties because it is a saturated liquid. Okay, with this, I already have enough information to solve and figure out how much Exergy is entering this plant. So it doesn't mention anything about kinetic energy. It doesn't mention anything about potential energy. So I'm just going to assume that all I have here is my difference in enthalpy and my difference in entropy. I know all those values. I know the mass flow rate, so I can plug it in. And I get that 21.98 megawatts of Exergy is entering this plant. That's not the amount of energy entering, it's much more, but this is the fraction that I can actually do work with. So now let's figure out the Exergy out. I'm going to let you more or less answer this. If I have 22 roughly going out and 5 turns into work, well, then I have 17 left. And if 7.5 is destroyed, well, I have 9.5 left. Guess how much Exergy exits? 9.5. That's all it is. We're just doing note keeping. The difference between my Exergy in and Exergy out is going to be equal to my work produced and my Exergy destroyed. Always. You can just add it up. And so, like I said, about 9.5. I rounded a little bit when I did it. So 9.38 megawatts. Okay. Last question. Actually, that's it. That's all this problem. So with this, hopefully you can see that we're dealing with Exergy. It's not all that scary of an equation. You just need to know the entropies and the enthalpies usually, and you can solve for the Exergy. Beyond that, just know that it's note keeping. Okay, just like this. You're going to have Exergy. It can't just magically disappear. It has to either be destroyed, or it's exiting, or it went into work. So something happened there. As a note, when we say Exergy destruction, we're talking about Exergy that did not do anything useful. We didn't produce any power with it. It just got wasted. So that's when we say Exergy destruction. So have a good one. I'll see you all later. Bye-bye.